Our last discussion was about the kinetic energy, but it began with a definition of energy where I said that energy is a number that you can calculate that has the remarkable property that it never changes or changes predictably no matter what occurs. So it's a number that you can calculate. So there's an equation, and we went through some algebraic hoops to come up with the idea that the kinetic energy, which you use the symbol capital K, is equal to 1/2 the mass of a thing multiplied by the speed squared. I claim it's really easy to calculate. 1/2 the mass in kilograms multiplied by the speed in meters per second squared, which gives you units of kilogram meter squared per second squared, which we call a joule of energy. We call it a joule of energy in biology and chemistry and engineering and physics everywhere. That is the SI unit of energy. The very last thing that I said was it's strange to call it kinetic energy when I had originally said that energy is a number that you can calculate that never changes, because the kinetic energy does change. If you travel faster, you have more kinetic energy. You travel slower, you have less kinetic energy. Well, I didn't say it never changes. I said it changes or changes predictably. So apparently the idea is a bit more sophisticated than that. So today, I'm just expanding our understanding of what is ultimately a larger picture. So this is, I think this might have been almost my next to last slide last time. I had done a whole bunch of algebra that led me to this complicated thing, which I certainly don't want you to be bothered by this complicated thing. Everything's going to be fine. The only reason I did it was so that I would get this thing here so I could show it to you. 1/2 mv squared, that's the kinetic energy. These are the units, a number that I can calculate. And in that moment, I'm sure I said, this here on the left-hand side, F parallel times delta x. Let's not worry about that for right now, because I just wanted to get the kinetic energy. But now I'm looking at the left-hand side of that equation, F parallel delta x, and I'm concerned. What is that? And the best I've done so far is to say, this is the parallel component of the force. What that means is the component of the force in the direction the thing's going, multiplied by delta x, which sure is displacement, but sort of philosophically it's space. I was asking the question, what does a force do in space, not outer space, in displacement? And so today I want to look at that left-hand side, that F parallel delta x, and see what it is that I'm talking about. Imagine that I have an object here, it could be like a box or something, I don't know. But in order to understand the way forces act on it, I draw sort of a pseudo free body diagram. Here's a box and I've exerted a force F on it. And you can, if you would not mind, look at this as horizontal and vertical, that would be fine. Upward, downward, leftward, rightward, that's fine. I've got this force and I can make two parts out of it, two components of it, because to consider it all at once is a little bit tricky, it's two-dimensional. So there are parts to it. The perpendicular component, which I've called F with the little perpendicular symbol there, and the parallel component of the force, which goes this way, and there's an angle here, the angle theta. Theta is a Greek letter, which is commonly used in physics and very often in math, to symbolize an angle. Now, there's going to be a little bit of trigonometry in our physics, but as is usually the case, we just work it out once, and once we've figured it out, we're done. And we just do that reliably. So what I'm going to do here, without worrying about like reteaching any trigonometry if we happen to be lacking, is to say that if I look at F parallel and F here and imagine that I fill in the space between these arrowheads, I have a triangle. And that triangle has an adjacent side, an opposite side, and a hypotenuse. And there's a relationship between the hypotenuse, which happens to be the force F, and the adjacent side, which is F parallel. And that relationship is cosine. It turns out I can always calculate F parallel by simply taking the whole force, however many newtons of force that is, and multiplying by the cosine of the angle. Once again, we're going to want to make sure that our calculators are in degree mode when we do that, or we may get some funny answers. Not wrong answers, but answers that we don't expect. I'm ignoring the component of the force that's perpendicular. What I mean by perpendicular here is I'm imagining that this box is going to move off to the right. I'm going to imagine that it moves off to the right in a straight line. The reason why the perpendicular component is of no interest to me is because it's not going to increase the speed. The perpendicular component of the force isn't in the direction that it's going. So that's not going to help increase the speed, or in the opposite direction, decrease the speed. But the perpendicular component will not change the speed, and so therefore is not going to have any effect on the kinetic energy. And that's what I'm interested in. Forces that are perpendicular to the displacement do no work. And work is the parallel component of the force multiplied by delta x. That's what I mean by work. Well, technically, I'm at work right now, in the sense that, in the very sociological sense, that I'm monetarily compensated for coming here and talking about physics. Joke's on them. I would have come here and talked about physics anyway, but I might as well have the paycheck. I'm at work right now. That's the sociological sense of work. This is the scientific definition of work. Work describes how a force changes the kinetic energy of an object. Now, this way I've written it here, that the work is F parallel delta x. That is very philosophical. A force in the direction of a displacement multiplied by a displacement. It's a very, very good scientific definition. It's not very useful if you're a student of physics trying to solve problems. So I take it and I make a little bit more practical by answering the question, what do you mean by F parallel? Well, I mean the component of the force that's in the direction the thing's going. So by F parallel, I mean F times the cosine of the angle. That's what I mean by that. Well, what do you mean by delta x? That's pretty fancy. I mean displacement, final position minus initial position. We know delta x. Maybe a little too fancy for our purposes. So let me just say, I mean the distance that you go. I mean the distance. As a practical matter, I mean the distance. So the work done is F cosine theta multiplied by d, but I have these parentheses, makes it look weird. I don't like it, literally, I don't like it aesthetically. It's all about how it looks. And so our definition of work, which instead of writing the word work, I'm going to use the symbol capital W. The work is the force times the distance times the cosine of the angle. The work is the force times the distance times the cosine of the angle. And I can calculate that if I tell you a certain number of newtons and a certain... And I can calculate that if I tell you a certain number of newtons, a certain number of meters at a particular angle. I can calculate that number. Here's the thing though, this number can work out to be negative. This number can work out to be negative. When I take force and multiply by distance, I'm getting a certain number of newtons and multiplying by a certain number of meters. So I get Newton meters as the unit for work. But it turns out that since a Newton is a kilogram meter per second squared, that a Newton times a meter is a joule. It's the same thing. So when I calculate the work, according to this new equation of mine, I'm going to get a number that's a certain number of joules. What it ends up meaning in the final analysis, that when I get a work that is a positive number of joules, it means I'm adding energy. Do you remember back to a lesson in linear motion when I was talking about acceleration, and I said that a positive acceleration means to add meters per second in every second, and a negative acceleration means to subtract meters per second in every second. That's a pretty clear idea. The same thing is true of work. When the work is positive, it means add these joules. Not every second, just add these joules. Got a pocket full of joules, positive work. Add these joules into the mix, put them into the recipe. But the equation, F times D times the cosine of theta, can work out negative. How could that possibly be? This is all positive, but it's not. The cosine is only positive between 0 and 90 degrees. If the angle is larger than 90 degrees, then the cosine works out negative. How could that be? Well, imagine that I draw a slightly different scenario where I have the same box, maybe it's sitting on a floor here like this, and I have a force acting on it where the force is opposite the direction that it's going. So here's the force, F, and here's the displacement, delta x, and the angle between them is greater than 90 degrees. When that happens, that's going to work out negative in your calculator. Now, mathematically, it looks a little bit obscene. as the angle becomes obtuse. But in terms of physical interpretation, when the work turns out negative, it means remove those joules. So positive or negative work is going to be really easy for me to get my head around. When the work is positive, it increases the energy by adding some joules in. When the work is negative, it decreases the energy by removing some joules. So here's my original equation back again, F parallel delta x. Well, I've just made that very practical. I've replaced that with the force times the distance times the cosine of the angle. That's what the work is. On this side, there's the kinetic energy, 1/2 mv squared, calculated with the final speed, minus the kinetic energy again, calculated with the initial speed. Well, that's final minus initial. So I could write it this way. The final kinetic energy minus the initial kinetic energy. That's the same thing. You see, this is the kinetic energy with the final speed, the kinetic energy with the initial speed. Why wouldn't I just call that delta K? The change in kinetic energy, just like the change in position, the change in velocity. Delta is a change quantity, and it's always final minus initial, and FD cosine theta is the work, and so I've created this majestic, fundamental, beautiful equation, which is known as the work-energy theorem. How fancy. The work-energy theorem, because it relates work and energy. It's got a good name. The work-energy theorem says that when forces do work, the kinetic energy changes. That's literally what that says. Work changes the kinetic energy. And that's what the work-energy theorem is all about. So here's my friend Slim, and he's pushing on a crate across a rough floor. And I've drawn a free body diagram here to show you what we all understand, that there are many forces acting. Look what I put on my free body diagram. There's the weight downward. The box is in contact with the surface, so I've got a normal force, a support force upward. Slim's pushing it to the right, but friction is acting to the left. What a sophisticated situation. When I apply the work-energy theorem to this situation, what do I mean by the work? Because I've got more than one force. Well, in a Newton's second law problem, on the left-hand side of Newton's second law, it says sigma F. What does it mean by sigma F? The sum of all the forces. It means that the acceleration is caused by all the forces. In the work-energy theorem, on the left-hand side, where it says work, what it means is the net work, the work done by all forces. So you'll find yourself not calculating just the work done by one force, but all of the forces. Don't worry, check out this little bit of awesomeness. If Slim is pushing on the crate to the right, and it's going to the right, then the normal force and the weight are perpendicular to the direction the crate's going. And perpendicular forces do no work. Perpendicular forces do no work. In my theoretical description, I said I'm going to ignore F perpendicular. And I'm still going to do it here. The normal force is perpendicular to the direction the crate's going to go. It does no work. The weight force is perpendicular to the direction the crate's going to go. It does no work. So I wrote here, the work done by the normal force is equal to the work done by the gravitational force. I wrote WG, the work done by gravity, is equal to 0. They don't do any work. So all I have to do is calculate the work done by Slim. Well, I know how to calculate work now. It's force times the distance times the cosine of the angle. But Slim is pushing in the direction it's going. So what's the direction between the force and the displacement? What's the angle? 0. Now, if this isn't automatic for you, you might want to train yourself up a little bit. The cosine of 0 is 1. The cosine of 0 is 1. So I did a little slash out here and just wrote 1. So really, the work done by Slim is force times distance. And then I calculate the work done by the friction. The work done by the friction is going to be the force of friction here, lowercase f, we typically use for the symbol there. Lowercase f multiplied by the distance, multiplied by the cosine of the angle. Here's the thing. The displacement is to the right, and the friction force is completely to the left. The angle between them is 180 180 degrees. And you might not have this memorized, you might want to train yourself up. The cosine of 180 degrees is -1. Well, Shadley, this has all become very mathy. Yeah, I get that. But I didn't need math to tell me that that was going to work out negative. The reason why is that I understand just from being alive that when Slim is busy putting energy in, positive work, Slim is busy putting energy in by doing positive work. He's putting joules in. Friction, and we know this, friction is taking joules out. It's taking joules out. Friction, bad. That's why you put wheels on the crate. Friction is going to take energy out. That energy that friction takes out appears as thermal energy. When Slim pushes his crate along, it's going to get hot, isn't it? Thermal energy is a form of energy. What do you mean energy? I mean, when you talk about how hot things are, there's a number that you can calculate. That's a certain number of joules. And when the friction takes the energy out, it warms the air. And those joules are now in the air, and the air drifts out the window and it's gone. The friction often, not always, the friction often does negative work because it removes energy. It's 100% okay to use equations to do math, but you can also think about the nature of things. Slim puts energy in, friction takes energy out, and what you get, the net result, is the sum of those works. So in a Newton's second law kind of a way here, I have the positive work done by Slim, which is force times distance, plus the negative work done by friction, so minus F times D, is equal to the change in the kinetic energy. Well, if I assume, just for discussion here, if I assume that the crate starts from rest, then it has no kinetic energy, because kinetic energy is 1/2 mv squared. If you're not moving, you don't have any, zero kinetic energy. So the change in kinetic energy, K minus K naught, the initial kinetic energy equal to 0, what I'm saying is that the net work would be equal to 1/2 mv squared, and just for fun, not for any practical purpose, but just for fun, I solved for V. Don't worry about the algebra. This is the impressive bit. Using the work energy theorem, I was able to predict the velocity in the future. Well, Shadi, I can already do that. We got that little equation that you love so much. V is equal to V naught plus AT. Yeah, but you have to know the time. Here I found the velocity in the future without knowing the time at all. I found the velocity in the future just based on how far it goes, not how much time. Well, I guess that's impressive to you, Shadi, but I really don't care. You will care, at a minimum, when you're required to solve a problem that doesn't tell you anything about time, but then questions what will the velocity be at some point in the future. One last little tidbit that sort of hangs on here like an appendix. Earlier in our course, I bestowed upon you 3 graph facts because interpretation of graphical data is useful in our scientific analysis. I said that the slope of the position time graph was velocity. I said that the slope of the velocity time graph was acceleration. And the strange one of those 3 is that the area under the velocity time graph is displacement. Well, here I've made a very simple graph of force as a function of distance. Force as a function of distance. Now, in our course, we deal with constant forces all the time. This can get ugly pretty fast if I let the forces change in time or change in distance. That the forces change as the motion happens, this can get weird very quickly. So I'm imagining a constant force here. What is this area here? Well, area is always length times width, which in this case is force on the vertical axis and distance on the horizontal axis. The area under a force distance graph is work. I've never before in my life referred to this as the 4th graph fact, but why not? Which, is this going to keep happening? Yeah, this is not the last time that I'll interpret a graph in terms of the physical quantities that I'm interested in this case, the work. The work which changes kinetic energy according to the work energy theorem.